Hi, I'm Jerry Shapiro. I'd like to introduce Dimitri. Dimitri is surrounded by a support team, his parents and Shelley, who have helped him move his ideas forwards. And welcome, thank you. Dimitri is a passionate young innovator, and he's the founder and CEO of Nephrogen, whose focus is to develop novel therapeutics for patients suffering from kidney disease. Like all of us, Dimitri has a very personal motivation because, as he will tell you, he has polycystic kidney disease, as does his mother, I believe. And so in order to help his family, he has developed a way of taking a patient's own cells and creating a kidney of their own cells so that it's biocompatible. There's no rejection drugs involved. It's a phenomenal achievement. But that's not his only achievement. So despite the fact he's only 17, he's already invented several biomedical technologies and is currently focused on bringing these to market. When he was 15, he invented a simple, rapid, patent-pending device to detect ovarian cancer. And actually, Shelley and I saw that device that he built himself without a 3D printer to scan. And then the following year, he invented this method for growing human kidney tissue from skin cells. He's currently working on a genetic therapy for polycystic kidney disease to cure the disease in its early stages and eliminate the need for treatment altogether. He received the top prize at the Maine State Science Fair in 2014 and 2015 for his work, and just recently won first place in the whole country at the Intel International Science and Engineering Fair, which is the world's largest pre-college science competition, and he won that this past May. In addition to presenting his work at contests, he's a scientist who's presented at work at several scientific conferences, including the American Society of Nephrology's Kidney Week, and is currently working to publish his work in a scientific journal. Dimitri is not only an astounding person, he's also a champion skier and a great and mature person. Thank you, Dimitri.
Thank you, Jerry, for that great introduction. I'm Dimitri. I'm a high school student. I go to school in, it's called Gould Academy. It's about 3 hours north of here, so I came down for the day to just talk to you guys about growing kidneys, essentially, in the lab. So I'm basically going to talk about the biomedical aspect of 3D printing and how we can kind of apply it to like organs and trying to grow functional tissue in the lab. And so I'll just spend some time talking about that. I founded a company this past August on Nephrogen to kind of bring this technology forward to the patient bench side. I'm a research assistant at Harvard Medical School, and I'm a senior this year at Gould. So the first thing I want to do is just kind of start with kind of an overview of the field, because everyone here is from mixed backgrounds. Some are in engineering, some are, and just kind of give an overview of regenerative medicine and bioengineering. So this is the definition of regenerative medicine, and basically what it is instead of using drugs and therapeutics to cure diseases, it's actually looking at replacing the organs themselves or helping them regenerate. And regenerative medicine is a really new field. It's only been around for 10, 20, it's a pretty new field, and bioengineering especially, like a lot of colleges now are starting to get programs for undergraduates in bioengineering, and that's WPI actually has a really good program for that now, and a lot of colleges are. But it's a very new program, very new fields, and I got really excited with it and started working on it. So now I'll talk about kind of what we've been able to do successfully with bioengineering tissues. And these are tissues that we've been able to successfully grow in a lab and actually transplant into a human. And what we have is the trachea. That was done by a group at the Wake Forest Institute for Regenerative Medicine. The bladder, also done by Wake Forest. The bone and muscle was done by a group at Harvard. And then reproductive organs. They were actually able to grow an artificial penis in a lab as well, which is kind of interesting. So I'm interested in kidneys, not penises or tracheas or muscles and bones. And I'm using stem cells to grow these kidneys, because stem cells can be isolated from patient skin cells, and I'll show And the 2006 Nobel Prize went to a group from Japan. Actually, I think it was the 2000. They did the work in 2006, but they won the Nobel Prize a couple of years later. And I'm specifically interested in induced pluripotent stem cells because what you can do is you can isolate them from adult cells. So I can take a skin sample from myself or any patient and use these 4 genes, OCT4, KLF4, SOX2, and c-MYC, to reprogram into stem cells. And these stem cells can then become anything in the body. They can become kidneys, they can become bladders, they can become hearts. And they're very similar to these embryonic stem cells, and there are some differences. So actually in my work I use both of these cells, but I focused on these because they're therapeutically and more clinically relevant. This is kind of the penultimate kind of summary of what I did. So I took the first step of the skin biopsy and I went through and I isolated the fibroblasts, then I reprogrammed the cells into these IPS cells, or induced pluripotent stem cells. And then after that, that's when my work came in. I differentiated them into kidney cells. I combined these cells with a 3D structure, and that's where you get into the bioprinting of actually getting the cells onto the, and then after culturing those together, you get your kidney that you can then transplant back into a patient. So the first thing I had to do was to turn these stem cells into kidney cells. So what I did is I started by studying how the kidney develops in the body. So I looked at basically embryonic development, and these are all the genes that are expressed at every stage of this development, and the mature cell types are shown at the end. And basically what I did is I treated these cells with different chemicals, and these are all the chemicals that I used through these 2 different protocols to take the cells through take the stem cells through these different stages of development. And these images here, I developed, the lab I'm working has developed 2 methods. I worked pretty much on protocol B. I focused on that one. And we also developed protocol A. Protocol B takes a little bit longer, but it's slightly more efficient. So I decided to focus on that for this. And I'll show the pictures of. These are the mature kidney cells. So this is day 19, so the protocol that I was working with. We get nice tubule structures that form that are characteristic of kidney that stain for those genes that I talked about in the other slide. So we have PAX8, cadherin 6, AQP1, all those different. And we have for the 4 different mature cell types, which is really interesting. So now that we have the cells, like kind of they're basically, you imagine they're growing in a culture dish. In order to get them to actually form tissue, you have to put them in a 3D environment. So my next step was to create a scaffold or a 3D structure to do this. And I actually used mouse kidneys to do this. So I took mouse kidneys and I used this detergent, sodium didecyl sulfate, to remove all the mouse cells. And you're kind of left with this, it's like almost a silk-like structure. It's just like this clear, it's comprised of like collagen and laminin and all the good extracellular matrix. So it has a 3D structure, but it doesn't have any mouse cells. And so this here, I just did some optimization with I looked at different temperatures and different concentrations of SDS, and I found that this one here actually is the optimal. As you can see, it's the clearest, it retains a good shape. And so I used that to prepare the scaffolds. And here you see DAPI stains all the cell nuclei. So you see that there's not, this is all really background stain, there's not any distinct blue dots that show that there's cells left in the scaffold. So that was good, and then obviously the red shows the laminin structure is intact, which is really good because that means I can put cells in there and hopefully get kidney structures. And so then I get into kind of the different techniques you can use for seeding cells. So obviously you can pipette the cells directly. So you can take a pipette and just put the cells directly onto these scaffolds. That's a very simple technique. It sometimes works. Gentle agitation, you can basically do the same thing. You pipette and then you just shake the scaffolds around to kind of get the cells to migrate in there. Then you have perfusion, which is when you actually run the cells through the kidney itself. So you take the renal artery and the ureter and you actually run the cells through this system. And that has shown, there's a paper in Nature Medicine that was pretty successful in rat kidneys, in rat hearts. And then obviously the big one is bioprinting. So that's kind of what the focus of, and this instrument here is about $130,000. They can go up to $300,000, depending on how nice you want it, how much control over things you want. And unfortunately, being in high school, I don't have the money to pay for a bioprinter, unfortunately. But I mean, it would be really nice to be able to test that out. So I actually ended up going up with the pipetting, because obviously pipettes are, I think, $150. So a couple zeros less on that number. So I went with pipetting, and it actually worked out quite well. Here I show the different structures that form in the, this is all really pretty technical stuff, but basically you see these nice tubule structures that I showed before actually also form in 3D. And AQP1 is aquaporin-1, which is a water transporter, so it's a functional marker that's present on kidney cells. And so that was really, really cool to see. We had that marker expressed, and we also had KSP, which is kidney-specific protein, which is specifically expressed on kidney cells. So that was good to see that we really had kidney tissue. And then in D, I show that the scaffold really is needed for these kidney cells, because the ones that are cultured in the scaffolds, the ones that are with the scaffold do express this marker, but the ones without do not. And then the DAPI is just stains all the cells, so basically all the cells express that marker. Then I went a step further, actually, and once I had this tissue that I'd grown in the lab, I actually implanted this into immune deficient mice. So they're mice that don't have an immune system, so you can put human tissue in them because I'm growing human tissue. So basically what I did here is I cut out a piece of we had a surgeon in the lab that did this because I couldn't get this right. But we take a piece of the mouse kidney out, and we basically transplant our scaffolds beneath them. And then we wait 4 weeks, and we monitor the mice's kidney function over time. We look at a bunch of different things to make sure it's surviving and it's healthy. And then we take the kidneys and we stain them for that same marker, that water transporter at the end. And here we show that this line here basically divides the human tissue from the mouse tissue. This is human nuclear antigen. So all these are human cells, all those are mouse cells. So you show that after 4 weeks, the human tissue looks very similar to the mouse tissue, and the mouse is surviving and doing really well. So that shows that my tissue can successfully contribute somewhat to mouse kidney function in vivo, which is really cool. And in conclusion, again, both protocols that I've developed can pretty do a good job of differentiating them into kidney cells. Some protocol B, like I said, is a little more efficient. And then obviously 1% treatment with SDS for 24 hours at 25 degrees Celsius effectively created the 3D structures. And when you combine them together by pipetting, that was successful, at least in this preliminary study, to do that. And then they could help contribute to function when I actually put it in mice. So in the future, there's some things I want to do, and I'm working on that right now. Going forward is perform some functional assays on the kidney cells, so to actually show that, because it's one thing for them to actually be able to survive and filter the blood, but it's another thing to show that they secrete vitamin D, they regulate blood pressure, they do all the other things that the kidney needs to do. And obviously the other big thing is the bioprinting aspect. I want to be able to take that bioprinter or get my hands on one, maybe WPI could help out with that. And basically combine and the nice thing you can do with the bioprinter is that you can actually combine that 3D structure and the cells together. So you can take that, the kidney structure that I created as a liquid and actually combine them together, and you can do different mixtures and seed them on, and so that you get a lot more control and precision with a bioprinter. And the last thing I want to do is perform an injury repair assay. So I've shown that these tissues could contribute to function in mice, but I haven't really proven it. I haven't really shown that I can injure the mouse tissue and then use my human tissue to regenerate that tissue. So that's what I want to do next. I want to really prove that this tissue is regenerating in the mouse and can someday be used on humans. And kind of the next steps for me, obviously, is this year, apply to college, and hopefully go somewhere cool, and continue working on all this good stuff. I've done a bunch of stuff with medical devices as well. I'm working now to license that technology, and obviously continue developing this. And I'm also, like Jerry said, I'm working on a genetic therapy to actually prevent polycystic kidney disease in my own, like as a therapeutic. So there's kind of 3 different product pipelines I'm working on with Nephrogen, and I hope to take those to the next step and bring them to the patients someday. So thank you.